it updates the BHT to say that for this branch, the branch is taken. Okay. So now you go to BQZ, again check, it's not 0. Therefore, you proceed to add and subtract. Jump loop now says taken because you have updated the branch history table. So it is a correct prediction. You will fetch BQZ, right? And proceed with doing the execution of the instructions. Now, when you come to R12 becoming 0 and you loop to BQZ, at that point, you will basically say that BQZ is not taken because that's still the value in the branch history table. So you will essentially end up saying that branch is not taken, but actually it is taken. So that's the second misprediction that happens. So that is what Bhaskaran Raman means when he says there are always two mispredictions in a loop with the single bit branch predictor. Okay, so I hope that's clear. If there is any, if there are any questions, I'll answer them. Now, one of the things you have to really speed up on is analyzing instructions. If you cannot analyze instructions, if you cannot actually draw the pipelining stages and analyze, what's happening, things will become difficult. Okay, so since the single bit predictor gives raw, misprediction twice for a loop, the next thing that is done is to make it a 2-bit predictor. And please note, here is a nice example of a finite state machine from your theory of computation course. Okay, so you have 4 states: strongly taken, weakly taken, strongly not taken, and weakly not taken states. So let's say we start in not taken state, then usually we start in 0, 0. If we say that we start in the 0, 0 state, then, if it is not taken, any branch is not taken, then we remain in that state. But supposing, let's say we are in the strongly not taken state and the branch is taken. Then we move to the weakly not taken state. Our prediction, however, still says not taken. Okay. So this works very well when you have, branches which go something like not taken, not taken, not taken, and then one taken, and then again not taken for a few times, right? Supposing you have 2 loops, one after the other, like for I equal to 0 to n and for j equal to 0 to n sort of loops, then, your for j loop will be taken a few times and then it will not be taken, right? And then you go to the for I loop, again come back and you will not take the for loop, you will take the for loop and then not take it. So this is the sort of pattern, that is when you have nested loops, that pattern is well captured by the 2-bit predictor. It's not captured well at all by the single bit predictor. So what you do, you start in the strongly not taken prediction. If the branch is taken, you go to the weakly not taken prediction, but your prediction still says not taken. Now, only if a second time the taken is done, then you move to the strongly taken. I think possibly let me check the finite state machine. Actually, where I'm weakly not taken, it should go to weakly taken stage, not strongly taken stage. So, then it basically takes 3 takes to move from strongly not taken to strongly taken state. And similarly, 3 not taken to move from strongly taken to strongly not taken state. That is the right state diagram. Let me correct this state diagram. So, we basically use this to change the prediction slowly. We don't change the prediction as soon as we hit one prediction which is different from what we are predicting, right? So that is the thing. And the examples that the Georgia Tech fellow has given will give you a understanding of how the 2-bit predictor improves upon the 1-bit predictor. So you can take a look at those videos, like I said, but I'll not put up those videos immediately because they start at a differentiation in the they start with a very different optimization on branches, which I haven't covered yet. Once I cover that, you can look at those videos. Okay, so this is the 2-bit predictor. So these are the two predictors which are covered in Appendix C of the book. Any questions on these? Because otherwise I want to take up the MIPS pipeline. I know we are running out of time, but I thought, you people should understand what's happening in the pipeline. The diagram, if you were to understand this diagram and the stuff on your own, that's why I'm actually talking about this. I do talk about it in my regular class also, but maybe not in so much detail because I expect students to read the textbook and understand and ask questions if there are any issues. So let's look at this pipeline. We start with the PC, right? We fetch the first program counter is loaded into the PC. So we send it to the instruction memory, which brings the instruction into the instruction register, right? At the same time, we are incrementing the PC so that the next PC is available to fetch the next instruction. So this is basically how we are incrementing the PC to immediately fetch the next sequential instruction. So this part is basically the instruction fetch stage, right? What's happening here? Here we are basically looking at the registers from the instruction register. You have done the assignment on, the instruction set architecture assignment, where they talked about 3 instructions with 2 operands and so on and so forth. You know how the operands look in the MIPS. There is a RS, RT, RD registers when you are talking about a register ALU operation. You can have a register immediate operation, in which case you have RS, RT and immediate and so on. Please go back and look at the various instruction formats of MIPS if you have forgotten. Now those particular bits, bit values are what are going into registers here. So you have RS, RT, RD. Okay. At the same time, you have an immediate which is sign extended. So you get the immediate value here. Okay. Now A and B are RS and RT. Okay. And if it is a register immediate operation, so that's why there is a mux here. The mux will basically be, selecting either this line or this line, depending on whether you're doing a register ALU operation or the register immediate operation. Okay. Now, if it is basically This is the branch condition that we are doing here. Okay. What we are doing here is basically determining whether this is a branch instruction, in which case you take the next PC and you have to add the immediate left shifted by 2. Please go back to your first, appendix A and look at them again if you have forgotten, but I am also going to show stuff soon. You're doing the branch condition evaluation here. Is it 0? If so, the condition is set, and the mux here will basically select between the next sequential instruction. This is PC that you have calculated here, and the branch target instruction address that you have calculated in the EX stage. So then it goes back to the PC from the mux. Okay. And of course, if you are doing load operation from the ALU output, or store operation, from the ALU output, you go to the data memory. If you are doing load operation, the effective address is given from the ALU and data memory is accessed, and your data is fetched into the temporary register LMD. And then you have the mux to write back the registers. Okay. So Bhaskar Raman also has the diagram, but differently, right? Okay. Let me just look at what happens in each stages, and then I'll stop. As I said just now, the instruction register is basically, you fetch the instruction from the PC location and store it into the instruction register, and calculate the next PC as PC plus 4 in the instruction fetch stage. In the ID stage, you say A is registers of RS. How do you get that? From the instruction register. Okay, you fetch the bits which correspond to the location of RS register value, and you read the register content of RS register into a temporary register A. You read the RT register content into temporary register B. You don't know whether this is you don't know yet while doing the decode if you're also to register values, right? So also assume that this may be a register immediate instruction, and so read the immediate field of the instruction register and sign extend it. Therefore, because you either have RS, RT, or you have RS and immediate in your instruction register, depending on what operation you're doing. So while doing decode, they also extract information for both, so that when you go to the execute stage, you can directly, have the immediate value or the RT value, whichever is needed. Now, in the execute stage, if it is a memory reference, you have to calculate the effective address. So that is done by doing A plus immediate, which is RS plus immediate. Register ALU operation, it is A of B, right? I have to put the space between A op and B. It can be the operation be any of these 4. It can be a load or store instruction, in which case you will calculate the effective address as A plus immediate. It can be a RU, in which case you will do A operation B. It can be a immediate operation instruction, in which case you will do A immediate. It can be a branch instruction, in which case what will you do? You will actually update your next PC value to NPC plus immediate left shifted by 2. You'll also evaluate the condition. In this case, they make the assumption that the condition that they are going to check is RS equal to 0. That's all. Okay, so that is what they are doing. Then you come to the MEM stage. In the MEM stage, you set the PC to NPC fetch. Memory reference, if it is either, if it is load, you basically, fetch the memory of ALU output to. I didn't show it. This is not correct. LMD is a mem of ALU output. Okay. And mem of ALU output equal to B for store. And if it's a branch, the PC is set to ALU output, which is basically, if the condition is true, then you're going to the target address. Okay. Now write back stage, you are going to write back the result of the operation. So if it's a register ALU operation, RD is the destination register. So you write the ALU output to that. If it's a register immediate instruction, then RT is the destination register. And if it's a load operation, you bring the value from whatever value you write from the memory, you write it into the RT register, which is the destination register. So these are the actions that take place. And now this is the same figure that we saw earlier, but with the pipeline latches now, which also Bhaskaran Raman talks about in his video, right? The pipeline latches are temporary registers which carry the results of the previous operation from one stage to the other, but they don't carry data from one instruction to the other. Okay, to carry data from one instruction to the other instruction, you need to use registers. Pipeline latches are only useful to carry information from one stage to the next stage. Okay, you can study this diagram. If you have any questions, we can answer them in the next class. All right. So this is what I wanted to do. I don't know. I'm assuming that this will be useful for you to get a real understanding of what's happening. These are the dependencies. The question is, what does the hardware do? How does the hardware detect that there is a dependence? How does it introduce a stall? What sort of logic does it use to determine that, for example, we said, add R1, add R3, R1, R2. R3 is the destination register. And then we say, if R3 equal to 0, how does the processor know that the branch is actually looking at a register which is, having dependency on a previous instruction? How is this dependence determined by the logic? And how does it introduce a stall into the pipeline? I thought it's nice to understand how this logic is done. So I have put all that sort of material into the slides. And then, of course, it's a question of how do you handle exceptions in the pipeline. So those are the two topics that are there. And then there will be the floating point pipeline, which introduces more complexities into the pipeline before we move to chapter 3. Okay. So any questions on what I have done? Okay, so we'll meet on Friday.